In this video, we will see some formulae that help us in calculating the magnetic field at the center of one single current carrying loop. Here in the top of the image here, see that there is a current carrying wire shown in blue color, and the arrows show the direction of the current, and the value of the current is given by I, and using the right hand rule it can be seen that the direction of magnetic field in all this region inside this loop, the magnetic field points up along the y-axis shown by the red color. That's what you can see using the right hand thumb rule, because the curling fingers are pointing upward along the y-axis. Also, if you were to look at these curling fingers outside this loop, the field will be pointing downward. This is outside the loop, and inside the loop the field points upward. This is inside. We know this from the loop, from the right hand rule, the thumb rule, but we can see another equation here that gives us the value of the field at the center of the loop. As you can find, this gives you the magnitude, and this is given by mu0 I divided by 2r. Please note that even though we are talking about a current carrying loop, here we don't have 2 pi in the denominator, it's just 2r. And the formula looks a little similar to that of a straight wire, but note that the pi is missing in the denominator. Now, what happens if there were to be another situation in which we have n circular loops carrying the same current I? So essentially we have a situation in which we have n such loops. They have the same radius and carrying the current shown in this direction. And then what happens to the magnetic field at the center of such n loops? For such a situation, this formula is applicable, shown here, that the magnetic field is given by n times the field of the individual loop. Remember, this gives only the magnitude. The direction needs to be obtained using the right hand rule. In the bottom picture here, we see the magnetic field lines due to a single coil, which was obtained using the right hand thumb rule. Now let us do a problem of calculating the magnetic field at the center of a single current carrying loop. In this picture, as you see on the right, there is a single current carrying loop whose radius is r, and it carries a current I equals to 3 amperes in the direction shown in the picture, which is the counterclockwise direction. So the formula for calculating the magnitude of the magnetic field is given by this formula, which we have already seen. We're going to put in the values of mu naught, the current, and the radius to get the value of the field. Now, important point is that the field points in a direction into the screen. This is using the right hand rule. right hand thumb rule. This is important. The thumb rule gives us the direction of the field, and the formula gives us the value of the field. Also, because the sign of the field can be obtained by knowing the direction that is going into the screen is conventionally noted to be a negative sign into the field. That's why our total magnetic field at the center, along with the direction and the value, is given by this. And of course we can show this direction using the symbols that we have seen, which is cross inside a circle. This is how the field will look like at all the points inside the loop, including the center. So that's the direction of the magnetic field. And outside the loop, the field will be pointing outward from the screen, shown by dots. You've seen this before. In the next slide, we look at the equation that is useful in calculating the magnetic field at the center of a current carrying solenoid. As you see in the picture here, there is a solenoid on the top right, and it is connected to a battery in which the current flows in this direction, like this. And as the current flows, it goes through the solenoid and comes back in this direction, and the blue arrows in the solenoid show you the current direction. We have already established that the field in the solenoid goes in this direction, in the center of the solenoid, from left to right. That's the field direction. We've obtained that direction earlier. Now the magnitude of that field is given by this equation. In this, the terms that we need to know is mu naught, permeability constant, and I is the current going through solenoid. The next terms is N, which refers to the number of turns or the number of coils in the solenoid, and L denotes the length of the solenoid. Please note here there is no R in the magnetic field equation for the solenoid, so we don't care about the radius of the solenoid. The field is independent of the radius. Now, sometimes this N over L factor is replaced by another factor, another variable. N over L gets replaced by a factor or a variable little n, and that is denoted as the number of loops per unit length of the solenoid. So depending on the question, if you may be given n, little n, like the density of turns per unit length, or the capital L and capital N. Of course, the direction of the magnetic field was already studied earlier. It comes out to be like this, using the right hand rule. In this slide, we calculate the field strength inside a solenoid using the equations that we have already seen in the previous slide. So we are given, the question asks, what is the field inside a 2 meter long solenoid? So this is the length of the solenoid that has 2000 loops. This is capital N. Here we are not given little l, little n. We are not given that, and carries a current of 1600 amperes. So this is I. Note here, we are not given the radius. As we noted earlier, we don't need R for calculating the field inside a solenoid. So we are using this formula. This formula is in terms of little n. Remember, little n is capital N divided by L that we defined earlier. So we just substitute that here, and then we calculate the field. Comes out to be 2.01 Tesla. In this slide, we see another variation of a solenoid-based problem. The question says, an MRI's solenoid is of length 1 meter. So this variable is L, which is given to be 1 meter, and has a radius of 0.5 meters. Remember, we don't need this because the formula does not have radius. The question says the magnetic field inside the solenoid is known to be 1 Tesla. So this is the variable B, which is used for denoting magnetic field. This is B. And the question says how many turns of wire must this solenoid have? So it's asking for what variable? How many turns? Remember, that is capital N. It's not little n, it's capital N. That's what it's asking for. We need to find this. Must this solenoid have to produce this field if it carries a current of 100 ampere? This is I. So the question is also asking to express the solution using one significant figure. We'll use up our equation rearranged to get N, the equation from the previous slide, and it comes out to be 8,000 turns. Now note here, in this problem we did not need the radius. Even though the question mentioned that, we want to be sure that we don't get confused. And we should not be using radius for calculating anything relating to solenoid.